For this next section, we're going to be going through 2.6, which is about operations and compositions. So we're going to do a couple different things. Really, it's kind of just about ways we can combine functions. So the first thing we're going to talk about is just kind of our basic math operations, adding, subtracting, multiplying, and dividing functions. And then the second thing we're going to discuss is composition, which is basically where one gets plugged into another. So when we talk about adding, subtracting, multiplying, and dividing functions, it's honestly exactly what it sounds like. If you see the notation f plus g of x, all that means is you take the function f and add to the function g. So whatever expressions you had before, you add them together and combine any like terms that you have. When you see subtraction, it tells you take the expression you have for f and subtract the expression you have for g. If you see a solid dot in between those, remember that's our multiplication. So I take f and I times it by g. And then if I see f over g, it just means take f and divide it by g. Okay. The thing we're going to be concerned about, because a lot of times we won't be able to simplify this if they're completely different. Like if I take a square root and I divide it by a cube root, I can't combine those together. They're kind of just stuck as is. If I were to add and subtract two quadratic functions or two of the square functions, I could definitely combine like terms, but I can only do so much when they're completely different. So one of the things that we focus on is finding the domain and range, or domains of this thing, not so much the range. So think about when you're dealing with two separate functions. When I'm combining them, I want to make sure I'm picking numbers that work for both of these functions. So if 2 works in f, but it doesn't work in g, there's no way I can actually have it in the function f plus g or f minus g. So for all of these, when we talk about finding the domain, we're looking for the overlap of g and f. So there's a short way we can write this is we take the domain of f, so all the values that work for it, and we take the domain of g, and we're looking for values in common, so we're taking what's known as the intersection. So this is finding common values between the two. So this symbol in the middle, union joins the two sets. This upside down one is the intersection of the two sets. So only the stuff that's in common. When we talk about division, it's a very similar domain. I still only want to pick values that work for f and g. But now, because you have an expression that's in the denominator, you also need to exclude the values that cause a problem. So this one's a little bit more complicated, but you still take the domain of f. You find the values in common with g. And then you also need to exclude values that cause the denominator to equal 0. So the way we can kind of write this as an intersection is we also find values that don't cause g to be 0. Okay. So what I want to do is just a couple short examples for this. We're going to work with two separate functions. I want to find the domains of both of them separately. Then I want to go ahead and find the expression for f plus g, f divided by g, and then I want to find the domains of each. Because honestly, the subtraction and multiplication really aren't anything different. It has exactly the same domain as this one. So I'm only going to focus on those two operations just to get something different. So let's start by finding the domain of both of these functions. Let's start with the domain of f. Remember, when we're dealing with a square root, we can't take the square root of anything negative. So we need whatever expression we have underneath that radical to be greater than or equal to 0. And then solving for x, for f, I can only pick values that are greater than or equal to -4. which in interval notation would mean I can take from -4 to infinity. The second I try to plug -5 into here, I would get the square root of -1, no longer gives me a real output. Now when we look at the domain of g, for this particular function, x minus 3, you have 0 issues. Nothing is going to cause a problem. Nothing causes us to divide by 0. Nothing causes the square root of a negative number. So really your domain is all real numbers. Everything works. There's no problems or no problematic numbers. Okay? So now when I go to find these combined functions using our operations, let's start with finding f plus g. We'll deal with the expression for both of these, and then we'll deal with the domain. All this means is take the function f of x and add to it g of x. So I take the function x plus 4 and I add to it the function x minus 3. And in all honesty, that's as far as I can take this. I can't combine anything else. I can't break the square root down. I have no like terms. This is as far as it goes. And exactly the same thing applies when we're dealing with division. We just take f of x and divide g of x. This is the square root of x plus 4 divided by x minus 3. Cannot simplify this at all. It is stuck in this form. Okay, can't magically multiply by anything to make things go away. This is where it has to stay. So let's go ahead and find the domains now for these combined functions. What I tend to like to do is I like to create a couple number lines. And so here, for this first one, we'll graph the domain of f, graph the domain of g, and this will give us what the domain of f plus g has to be. So looking at these two expressions, really -4 is the only number that appears within these. So that's the only number I'm going to graph on both of these, or all three of these. For our function f, -4 is our first important value. We can equal it, and then I can pick all values greater than this. For g, we have 0 issues. We get to equal everything. So now when I go to combine the two of them, I want to pick values that work for both. So looking at these, in both of these expressions, I can equal -4. So that means I can equal it in my combined function. On both of these, I can shade to the right of -4. So in my combined function, I can shade to the right. However, to the left, I can't plug in these values for the top function. So in this combination, I cannot shade to the left. So the domain of f plus g is going to be from -4 to +infinity. Okay. And then again, if you were to find f minus g, same domain. If you were to find f times g, same exact domain. What changes is now over here because we introduced the variable in the bottom. So immediately I have a new problem. I now also can't have +3 as one of my values for x. So this is a new issue that arises. Okay. So when I go to create the domain for this, I can use exactly what I've done before. I'm going to use this domain because it's the numbers that work for both of them. But in addition to -4 being important, +3 is important. So we are able to equal -4, but I cannot equal 3. So my domain is everything I had before except this exclusion of +3. So in interval notation, this would be -4 to +3. and then 3 to infinity. Okay. Let's try our next type of operation, which is called composite functions. And so often you'll hear this referred to as fog or golf. It looks very similar to multiplication, but you have an open circle here. And so what this means, if you see f of g of x, you're going to compose g with the function f. So f is on the outside, it is the outer function. G is on the inside, it is the inner function. So what happens is I'm taking f and I'm evaluating it at the function g. Okay. So I take g of x, it becomes the input into f of x. And then each of these have their own names. The domain for this is found in a very particular way. So only two functions are going to matter, and that's going to be this input. So you always start by plugging x into g. So the domain of the inside function is important. So I look at the domain of g. Okay. Function f is not going to matter at all in finding the domain. Instead, depending on what expression you get, you need to find the domain of that and take the numbers in common. So you find the domain of g and you find the domain of your final expression or function, and you find the numbers common to these two. So f's domain does not make a difference at all. Okay. So let's try an example. Given function f and given function g, let's find f of g and its domain. Okay. So again, all this notation means is I'm taking f and I'm evaluating it at g of x. Okay. So think of when we did this before. G of x is the square root of x plus 2. So I'm taking this outer function, and anywhere I see an x, it's getting replaced by the function g. So this really becomes 1 over the square root of x plus 2 squared minus 1. Okay. And then from here, we can do a little bit of simplification. Square and square root cancel each other out. So we get 1 over x plus 2 minus 1. And then simplifying one last time, plus 2 minus 1 gives us plus 1. So you notice that our square root function ends up disappearing in this final expression that we get. But the square root is still important, because anytime I'm talking about domain, I want to make sure every expression along this equal to makes sense. So when I find the domain of this composite function, I have to find the domain of g. Okay. I've got to make sure this expression is defined to begin with. So one thing I need to make sure for this composite function is that I have x plus 2 being greater than or equal to 0. Which is the same thing as saying x is greater than or equal to negative 2. So right off the bat, I cannot pick values that are smaller than negative 2. Even though in this end expression, it doesn't seem like that would pose an issue. I could plug negative 10 in here, no problems. But again, I can't plug negative 2 back at this step, so I cannot plug it into this function. Right? So I find the domain of the inside function. Then I need to find the domain of this final expression, which is the 1 over x plus 1. So the only issue we have here is we can't plug negative 1 into this expression. Okay. Now I want the overlap of these two. So now we can actually go ahead and find the domain of the composite function. And again, I'm going to draw 3 number lines just to get a little bit of a hand. So I'm going to draw the domain of g. I'm going to draw the domain of the end expression we got. And then I'm going to go ahead and that will give us the domain of the composite function. So between these two, I have two important numbers that have appeared in each of my domains, -2 and -1. So I'm going to graph these on every single number line in order. Okay. So first and foremost, for G, first value I can equal is -2, and then we can equal anything to the right. Then when we go to the end expression we got, -1 is an issue, but nothing else was an issue. So for the composite function, I want what's in common. So both of these values can include -2, so I can shade that in. But the top or the bottom one cannot equal -1, so I cannot equal it for this composite function. Okay. I can shade in between these two numbers for both of them, so I can shade in between the two numbers for the composite. I can shade to the right indefinitely on both, so that means we can do that over here as well. However, I don't have both of these intervals shaded in, so I cannot shade it in for the composite function. So our end result for the domain would be from -2 to -1, not equaling it, and then from -1 to infinity. So do your best with these. It's definitely complicated, so don't worry if it takes you a little bit of time to get used to them. Instead, what we're going to do is we're going to focus on other types of problems to get more familiar with compositions and then also with our operations. So for this next example, we're going to use the chart to evaluate the expressions. So they tell us for these x values, here's what f equals and here's what g equals. So for our very first one, what we want to do is I really want to find what is f of -2 and add to it g of -2. So using my chart, when x is -2, f is -1, and g is 5. So this is really -1 plus 5, which then we add together and it gives us 4. Okay. For the second example, this is really, again, multiplication. So this is saying take f of 2 and times it by g of 2. So using our chart, when x is 2, f is 4, and g is -3. So this ends up equaling -12. For these next two, we have compositions. So again, remember the order does matter, which comes first and which comes second. This composition tells us take g of f of 2. And our order of operations tells us to work from the inside out. So first, I need to find f of 2 using our chart. Well, when I plug in x is 2, f of 2 is 4. So this is really saying evaluate g of 4. Then from here, I use the chart again. When x is 4, g is 3. So this ends up equaling 3. So for compositions, we've got to take it piece by piece. Same thing for this example, even though we have the same expression, this is saying find f of 2. So let's erase all of our markings we have on our chart. I've got to start with the inside first. So I need to use the chart to find f of 2. When I plug in 2, f is 4. So the inside can be replaced by 4. And now using our chart again, when x is 4, f is 10. So this ends up equaling 10. So you start with the inside, evaluate that, then you go ahead and evaluate the outer function of whatever you found simplified from the inside. Let's do a very similar example, but now instead of using a table, we have to utilize the graph. So for this first one, subtraction just says take f of 3 and subtract g of 3. So when x is 3, g is 2, and f is 0. So f of 3 is 0, and g of 3 is 2. So this is just 0 minus 2, or negative 2. Okay. Moving on to the next two, again, this is composition, so I gotta do the outside is g, the inside is f, and we're plugging in 1 for x. So I've got to start on the inside by finding f of 1. And using our graph, when x is 1, f is 2. So the inside is really 2. And then using our chart again, when x is 2, g is going to be 0. So this ends up equaling 0. Okay. One last one, but now we're reversing it. F is on the outside, g is on the inside, and we're evaluating this at 2. So starting on the inside, we actually already did g of 2, but that's okay. When I plug in 2 for x, g is going to equal 0. So this is f of 0. Okay. Now using our chart again, I've got to see when x is 0, what is f? And that's right up here. F of 0 is 3. Okay. So take everything step by step. Remember, you're evaluating one thing at the other with compositions.